So, for our first application of the Heisenberg uncertainty principle, what I want to think about is the uncertainty and how it evolves after a certain amount of time t. So, uncertainty after a time t. And I'm going to pose this as a question. So here's the question. Let's suppose an electron is placed very carefully, and in a moment you'll see what I mean by very carefully. We're going to try to optimize something. It is placed very carefully at a given location at time t equals 0. The question then is, what is the minimum uncertainty t in the location of the particle after a time t equals 1 second. And in terms of the uncertainty after that time, what we could symbolically denote that as delta x, the way we usually characterize uncertainties, but I want to know what delta x is not at time t equals 0, but at this future time t, whose value we will take to be 1 second, in looking at the example of an electron. So now, here again is the basic idea of what's going on. So the idea, of course, is that, well, we want to place this particle at some location, say x naught, and we're going to prepare it there as carefully as possible. And because we want to know where the particle is going to be at some time later, of course, we want to prepare the particle in such a state that the probability distribution for finding the particle at that initial time t, this is still all at time t equals 0, there will always be, as we've learned from Heisenberg uncertainty, a certain uncertainty at the initial time. And I'll call that initial uncertainty delta x. Now, there's of course some tension here between the uncertainty in the position and the uncertainty in the momentum. So if we look at the probability again, initially at that time t equals 0 point, for the momentum of the particle in the x direction, what we know from Heisenberg uncertainty is that this can't be 0. Now we're going to be preparing the particle as carefully as possible, so we're not going to give it a state where the distribution of momenta has a non-zero average, but still there's going to be some distribution. We will be careful to center it near 0, but there is still always going to be some uncertainty in that momentum, delta px and naught, because that's the initial uncertainty. And now you can see really where the tension arises. To really know where this particle will be at a time t later, we want to make this uncertainty in the initial position as narrow as possible. But the more narrow we make that via the Heisenberg uncertainty principle, there will be a correspondingly large uncertainty in the momentum, because the momentum uncertainty is going to be h bar over 2 times delta x naught. So the tighter we make our knowledge of the initial position of the particle, the broader the momentum will be. And if we have a broad momentum, there's going to be a broad range of velocities for this particle. And after a time of t equals 1 second, if this is very broad, we'll have no idea really where the particle was. So that's the basic concept or idea. So let's try to make this a little bit more mathematical so we can put some limits on things. So the math that goes along with this would go as follows. The position of our particle at time t, we can say, of course, will be its initial position, whatever that initial position was. So really, I should redraw my axis like this. So this is the axis that tells me the initial position, and this is the axis that tells me the initial momentum in the x direction, right? So it's going to have some initial position. I don't know what it is, right? It's centered on this point where I'm hoping to keep my particle localized. So it starts with some initial position that has some probability distribution with it and some uncertainty in it. But then, after time t, of course, it's going to move along according to its velocity. Its velocity will be this unknown initial momentum, which also has this spread associated with it, divided by the mass. That gives me the velocity. And then, of course, to find out where it ends up, I have to take the initial position plus the velocity times the time t. Now, here's the issue. I have uncertainty in both of these variables, the initial position and the initial momentum, and I have a way of characterizing that. And I have to determine then what those uncertainties tell me about the uncertainty in this final random variable, which is the position after a time t. So I would just like to help us analyze that. I'd like you to recall something from our lecture notes on from the class notes on statistics, and this had to do with what happens when we add random variables. So if we have a random variable a, which is the sum of two random variables b and c, there was this very powerful theorem which tells us that the variances will add if the two quantities we are adding are statistically independent. And this is if b and c, these random variables, are statistically independent. Now, in terms of the language that we are using for the Heisenberg uncertainty principle, remember the variance is oftentimes written as sigma squared a. It's defined, the variance is defined as the square of the standard deviation in a. And likewise, the variance of b is the square of the standard deviation of b, and correspondingly then for c. And then finally, I'd like you to notice that the standard deviation is what we typically call delta x or delta p when we're using our precise definitions for the Heisenberg uncertainty principle. So the conclusion from that little diversion we've just had is that the uncertainty in delta x at time t squared, right, because the uncertainty corresponds to the standard deviation in that quantity, will be if I assume, and this is a physical assumption we are making, that the uncertainties or the fluctuations that we see in different positions are indeed uncorrelated with the uncertainties in the momenta. And later, when we have our more formal theory, you will see that, in fact, this does carry through, because you can actually do this analysis with a formal wave packet, and you will come to precisely the conclusions we're coming to here. Now, following along with my equation here, that would then be the uncertainty in my initial random variable, delta x naught squared, plus then the spread or standard deviation in this quantity. Now, this quantity is just a constant times my random variable p naught. There's another theorem that goes along with this, which just says that the standard deviation of a constant times a random variable is, of course, just a constant times the spread in the random variable itself. In other words, this factor is just scaling the size of my random variable. So I just get back that constant, and then times the uncertainty in my random variable. So the total standard deviation here is going to be t over m times delta p naught, and that quantity, of course, has to be squared according to my formula for how I combine uncertainties. Now, by the way, there's a nice mnemonic for remembering how standard deviations combine in random variables. As you can see, of course, this looks a whole lot like the Pythagorean theorem. So rather than just having this equation, one could, of course, have a nice little diagram to go along with it as a mnemonic, and that is whenever I have different random variables, I can draw this right triangle, and the uncertainty then in delta x of t should just add like the Pythagorean theorem in terms of the uncertainties in these other variables. So over here I would have the uncertainty in x naught, and the uncertainty again in p naught times t over m would just be t over m times the uncertainty in p naught. Very good. So now we have a good handle on what this final uncertainty is. What we want to do is to prepare our particle as carefully as possible. In other words, we want to find out what is the absolute physical minimum limit on the quantity that I'm showing to you here. Now, of course, one thing we can do is control delta x naught and find an appropriate value for that. We will do that momentarily. But the other thing we can do is that for whatever value of delta x naught we've chosen, we make sure to choose the most appropriate state so that we have the least possible contribution coming from delta p, right? This quantity is always going to be greater than or equal to what will happen if I put the minimum possible value in for delta p naught. And as we said, to minimize things, what we would want to do is to choose delta p naught actually at the minimum. It would have to assume the value h bar over 2 delta x naught. So this is going to equal, but at the minimum, I can then replace delta p naught with the Heisenberg limit as h bar over 2 delta x naught. And when I do that, then my result will be, let's move this down a little bit, will be delta x naught comes in two places. The initial term plus then I have, and what I'd like to do is I'm going to substitute this in, and I'd like to pull out all of my factors right now. So I'm going to have h bar, which goes in here, times t, but they are both squared. So I've got h bar squared, t squared, divided by 4, because 2 gets squared, and then m squared. 4m squared times 1 over delta x naught squared. So that's the best we can do. That will be at the minimum if we do our best by the momentum. But we now also have to choose what the best value for x naught would be. And again, we can see there's the same tension between the position and the momentum effects, namely these two terms. So if we were to make a plot of this, so I'm plotting for you then the resulting delta x squared at time t as a plot of how we place our particle as characterized by its value of delta x naught. Or I could do this as delta x naught squared if I like. And what you'll notice is when delta x naught squared is tiny, this term will dominate, and I will be going up towards infinity as delta x naught squared approaches 0. So it's going to come down like this. And then when delta x naught is squared is large, it will dominate over this other term, and I'll just have something that's going up like a straight line, right, of slope 1. Delta x squared equals delta x naught squared. So I will have a function that looks somewhat like this. And what I want to do to very carefully place my particle is I want to choose the delta x naught that characterizes the state in which I put my particle to have this particular value that yields this minimum. So there's a particular optimal minimum value for delta x. I'll call that delta x star. So to minimize this quantity, I think we know what we would want to do, right? We will have to take the derivative with respect to delta x naught and set that equal to 0. So 0 will have to be the derivative with respect to delta x naught. And the function I'm taking the derivative of is the function that you see up here. And just as a shorthand, I will write, the quantity that I'm actually minimizing. But we know how to take its derivative with respect to x naught. I just have to proceed in the usual way. The derivative of this term, I've got a sum, so I've got the derivative of the first piece, which would be just 2 delta x naught. I then have the derivative of the second piece, which will have a minus 2, because I've got 1 over delta x naught squared, so there will be a minus 2. I then, of course, have all of my constants from before, h bar squared, t squared over 4m squared. And then I have 1 over delta x naught to the next power, which is, of course, delta x naught cubed. And what I want is I want this combination to give me 0. And so now it's a simple matter of solving for delta x naught. And we can do this in two steps. First, we can see these two terms add to 0. I can certainly cancel out the factors of 2. That's pretty easy. The next thing I would do is I would move this to the right-hand side of the equation, where it will come in with a plus sign. And then that will give me delta x naught on the left-hand side will equal then all of these factors. But I might as well get all of the delta x naughts together. So this 1 over delta x naught cubed I will multiply by, so that will give me delta x naught to the 4th. And what that must equal are all these terms that are left over, h bar squared, t squared over 4m squared. Now, the final task, of course, is we want to know what is actually this minimal possible uncertainty. And I should say, what we've been solving for here really was the ideal choice for delta x naught, which we had decided to call delta x star. So excuse me for that. We'll call this delta x star. So I now have to substitute in my result for delta x naught star. But you'll notice my result is in terms mostly of delta x star quantity squared. That's what we have to substitute in, but that's easy enough to solve for. I can take the square root of both sides. So for the ideal delta x, the square of it will just be ht over 2m. And then my job is to find then this minimum possible delta x, the minimum possible value after this time t of 1 second, squared is what we have on the right-hand side, will be delta x naught squared plus this second term, but delta x naught squared, I've got a pretty good handle on. That's right over here. That will be h bar t over 2m. And then the next term is plus h bar squared t squared over 4m squared times 1 over delta x naught squared. So I have to flip this one upside down. Oh, this is getting interesting now. That's 2m over h bar t. And why I'm thinking this is interesting is notice there's a lot of beautiful cancellations, right? I've got an h bar t factor down here, which can kill one h bar and one t. My m up here can cancel one of these m's. And my 2, of course, can turn my 4 into a 2. And what I notice is I have just two identical factors of ht over 2m. So when I add those together, I get very simply ht over m. And now we have our final result. So the least possible uncertainty that I can have in the position of this electron after time t, no matter how carefully I've placed my object in the most careful way possible, will be the square root of h bar t over m. Great, that's a nice general result, but we had actually a specific example, so we should put some numbers on this. So for us, in our example, and this is useful to go through because there's certain fundamental constants we want to carry around in our head, and to help us do a little mental math. So delta x min at our particular time t equals 1 second is going to be, by the preceding formula, h bar. Now h bar has an interesting value. As you know, h itself is 6.6 times 10 to the minus 34th joule seconds. And it's always nice to see the units work out. So remember, a joule is a kilogram meter squared per second squared. But because the units on Planck's constant are joule seconds, instead of over seconds squared, I just have over seconds. That gives me my h. To get h bar, recall that we divide by 2 pi. And here's kind of my point now. I want you to notice that 6.6 is pretty close to 2 pi, right? Pi is 3.14, right? So 2 times pi is going to be about 6.3. So I have 6.6 over 6.3. I'm off by 0.3 over 6. That's about 1/20th or 0.05. So this, my point is that h bar has a value that's very close to simply 10 to the minus 34 kilograms meters squared per second. If you want to be a little more precise, it's about 1.05 to give you slightly more precise values. But for an order of magnitude estimate like this, I'm very happy actually just to use the 10 to the minus 34 value. So that's some useful information about the value of h bar. We also had to multiply by time t, but I chose a nice time interval of just 1 second, which is very nice because now I see my units are starting to work out. My seconds cancel each other. Now in my denominator, I have another key value. I have the mass of the electron, which you will recall is 9.11 times 10 to the minus 31st kilograms. Now, once again, units, you can see, are going to work out nicely. My kilograms will cancel each other, so I will definitely be getting now an answer in square root of meters squared. So I get meters. That part is very good. And what's left under my square root you can approximate pretty well, because I want you to notice about the numerical value of the electron mass. 9.11 times 10 to the minus 30 is actually, pretty close to a nice round number of 10 to the minus 30 kilograms. So if you can carry around in your head the mass of the electron is 10 to the minus 30 kilograms, and Planck's constant h bar is about 10 to the minus 34th joule seconds, you can make a lot of very useful estimates very quickly. Now, what's left for us is we do this division. I won't worry about these, slight differences between 1 and 0.9 and whatnot. I just have basically powers of 10. 10 to the minus 34 divided by 10 to the 30 is 10 to the minus 4. And 10 to the minus 4 square root is just 10 to the minus 2, 0.01 meters. In other words, 1 centimeter. So that's kind of remarkable, actually. This is kind of getting interesting, right? So the idea here is, I could have some table or something, right? And I'm going to place my electron, as carefully as I can at one particular location here on the screen, doing the absolute best I can. And then I turn my head, right, for 1 second later. So 1 second later. So this is t equals 0, right? I just place my electron carefully. And 1 second later, I've got no idea where this electron is, right? I just know it's somewhere within a radius of about 1 centimeter. It's a really observable macroscopic distance. And what's really neat is the location of the particle within this region then becomes completely random. Right? There's no process in the universe that could predict exactly where this electron is going to land. Of course, notice we're assuming here there's no external fields or forces acting on my electron. But still, it gives me this complete randomness in a way that I could potentially measure. And this leads us to consider the idea of the design maybe of some kind of perfect gambling device where we could use effects of quantum mechanics to ensure that we have a perfect way of generating random positions and random numbers simply from using quantum mechanics. Very good. So that then wraps up our first example where we're dealing with the consequences of the Heisenberg uncertainty principle and what happens in systems as they evolve in time.